Hey guys, this is test 56, game 3. This is the tree plantings game. It is what I call a splitting game because we are dividing the variables here, most, into one of two groups, G and L. Of course, the variables could repeat and go into both groups here. I've laid out a bunch of rules here, I'll explain all of them. We've got each park with exactly 3 trees, so I put 3 spaces under each park, G and L. They tell us that at least one park has both M and S, so I put 1x or 2x once or twice next to the MS vertical box here. They tell us that whenever we have O, we will have both O and T. And finally, they tell us that G has M. So, very bare bones initial setup here. However, there is actually a lot we can do to create multiple main diagrams and take care of all of this game's work up front. It's the rule here that MS occurs once or twice. We could have MS on G, but not on L. We could have MS on L, but not on G, or have MS on both G and L. So here we have MS on G, but not on L. We have MS on L, but not on G, and we have MS on both G and L. So I indicated that MS could not be on L by saying, we can't have both there. We could have only one though. On the second diagram, since we have to have G on L, M on G, since M is always on G due to the last rule of the game, I indicate that S cannot be there. And because we only have 4 types of trees here, things are actually very limited. In any scenario where we already have MS on a particular park, we cannot have O there because O would require T as well, and there's no room for that, given that there are only 3 trees per park. So in the first diagram here, since O can't go there because then we'd have to have T also, and we need a third tree, therefore we're simply going to have T there. And that goes for all of the parks in which we have both M and S. We can't fit both O and T, and O requires T. Therefore, we'll simply have to have T without O. In this diagram where we don't have both M and S, we will have to have exactly one of the two due to the fact that there are only 4 kinds of trees, and then we will have O and T as well. Now in this one here, we have M, we can't have S, therefore we'll simply have both O and T, and every single diagram is completely filled up, leaving virtually no ambiguity at all here in this game. This game is incredibly simple once we lay it out, using MS to create multiple main diagrams. We have only a total of 4 valid scenarios here. The one on the right has 1, because there's no ambiguity. The one in the middle has only 1, and the one on the left has either M on L or S on L, but no other ambiguity. So things are virtually completely determined here, very simple. We'll start running through the questions. Looking at number 12, typical orientation question. Just take one rule at a time and apply it to all 5. We know we've got to have MS occurring at least once, so let's look for scenarios where MS does not occur at all. Let's see, we've got MS in choice A, we've got MS in B. No, we don't have MS in B. We have MOT on both diagrams in B, therefore B is unacceptable and can be eliminated. The other diagrams are good on that issue though. We know we've got to have O requires T as well, so any scenario with any park with O has to have T also. That eliminates A where we have O but do not have T. The other choices are good on that issue though, except for C actually. C has O in landing, yet does not have T there, therefore C is gone as well. Now, we know that G has to be on M, so any choice without G on M is gone. That gets rid of E, leaving D by elimination for number 12. Next, number 13, general must be true question. We'll just run through the choices here. Does G have to have S? Not in the middle diagram. In the middle diagram, G does not have S. It has MOT, therefore A is automatically eliminated. Next, looking at B, L has M. Happens in the second and third diagrams, but in the first one, it could have SOT, lacking M altogether, therefore B can be eliminated. Next, looking at C, L with T. Happens in every single diagram. L always has T, therefore C is our answer to 13. I will look at D and E though. Number of parks with maples is equal to the number of parks with S's. So do we always have M equaling S in terms of quantity? Happens in the diagram on the right, but not in the middle diagram where we have 2 M's and only 1 S. Therefore, choice D can be eliminated. If you look at the diagram on the left also, we could either have 1 M and 2 S's if S were chosen for L, or we could have 2 M's and only 1 S. Therefore, they do not have to equal each other, and D is gone. Then looking at E, M greater than S happens in the middle diagram. In the one on the right they are equal though. Additionally, in the diagram on the left, we could have two m's and only one s, or two s's and only one m, so m does not have to exceed s. E is gone, leaving C by elimination if you didn't get it before. Next, number 14, if both parks had sycamores. So the middle diagrams are relevant since only L has sycamores there. And in the diagram on the left, we're going to choose S for landing rather than M, and the left and right diagrams are the relevant ones here. What could be true? M equals O. On the left, we have only one M and one O, so they're equal. And on the diagram on the right, we have M exceeding O because there are two M's and zero O's. Yet in the left diagram, it could happen, therefore A is our answer for 14. I will look at the rest though. M greater than S, here they're equal. Here S is greater than M, therefore it does not happen, and B is gone. Looking at C, O equals S in quantity. They're not equal here where there are two S's, zero O's. Here two S's, one O, not equal either time, so C is gone. G with both M and O happens in neither, where G simply has MST for certain, so D's gone. Looking at E, L with M and O. On the right it has MST, on the left it has SOT, never both M and O, so E's gone as well, leaving A. Next, number 15, general must be false questions. So we could look for the four things that could be true and eliminate them, or if we see something impossible, just pick it and move on. So A, both with oaks, never happens. At most we have one oak between the two parks, never oaks on either side, so A is impossible and is our answer. I'll look at the rest though. Both have sycamores, happens on the right for certain, could happen on the left diagram as well, so B's gone. Both with T, happens in every single scenario, so it actually must be true. So C's gone. D, exactly one with M, happens on the left. We could have S on L and SOT without M altogether, and then the only M would be the one on G, so D's gone. Then E, exactly one S, happens in the middle diagram for certain, could happen on the diagram on the left if landing had M, therefore E's gone as well, leaving A. Next, number 16, general could be true question. O equals T. No, we always have two T's and always have one O, therefore they're not equal. O greater than S. We have two S's here, zero S's, and then here they're equal. Here S's could exceed O's. But we never have O greater than S because there's only one O or zero O's, and there's always two S's or only one S, so B's gone. Only one T, well, we always have two T's no matter what, so C's gone. Neither with T's impossible because we have two T's at all times. And then by elimination E. And if we look at it, E is saying that we have both parks are identical. Happens in the diagram on the right where both have MST, therefore we know it's possible, so E.